Welcome. In this video, we're going to start looking at acids and bases. So this is from section 18.1 of our Glencoe textbook. Acid and base are two of the most common classifications for a substance, and every substance can be classified as being acidic, basic, or neutral if it's neither. So acids are found in many of the foods we eat, helps in digesting our food. Hydrochloric acid, which we often use, is present in a very dilute or weak amount in our stomachs. And bases are found in antacids when we have too much stomach acid, as well as many household cleaners. So they're all around us all the time. Some properties of acids and bases. Acids taste sour, so lemon juice is a common one. Sharp or tart is another way to describe it. Well, bases tend to taste bitter, like coffee. And bases feel slippery. So if you've ever used a household cleaner and afterwards your hands feel really slippery, that's a base that's making them feel slippery. Both acids and bases are good conductors of electricity. Pure water is actually a fairly poor conductor because unless there's some electrolytes or ions in there, the conductivity is very low. Another property of acids is they react with many metals. Some metals, the more reactive metals, they react more with. All aqueous solutions contain hydrogen ions and hydroxide ions because if you think about it, water contains both these ions. It's really, instead of thinking of water as H2O, especially as we do acid bases, I tend to think of water instead as being HOH. So it's still neutral because you've got a positive hydrogen ion and the negative hydroxide ion, but that's what water really is. And some of those water molecules will fall apart into the H plus and the OH minus, which we'll talk about later in the chapter. But in a neutral solution, you would have equal numbers of H plus and OH minus because each water molecule has one of each. So it's not like it can fall apart into two OHs or two H pluses. It's always going to fall apart into one H plus and one OH minus. So then when H plus outnumbers, when the hydrogen ions outnumber the hydroxide ions, that's when solutions begin to behave as what we call acids. And when there's less H plus or more OH minus, whichever way you want to think of it, when there's more hydroxide, that's when substances begin to act like bases. And that's really all an acid and a base is it's the amount of H plus or OH minus in the aqueous solution that gives it these properties. Seems pretty minor for as destructive as acids and bases can be. So the simplest model of acids and bases comes from a Swedish fellow named Arrhenius, and he said an acid donates H plus when dissolved in water, and a base donates OH minus in water. And a neutral substance donates neither H plus or OH minus. And this model actually works well for lots of acids and bases, but not quite all of them. So it misses a few, plus technically a neutral substance can donate H plus and OH minus, it just donates equal amounts like water does. So when doesn't this model work? Well, for example, ammonia, NH3, when it gets together in water, it tends to take a hydrogen from water, so it leaves an OH minus behind, and it becomes NH4 with the positive charge, or ammonia. So that doesn't fit. How does that work? It makes water the acid here. And so then Na2CO3 has a similar issue that it doesn't have a hydrogen to donate or an OH, and yet they both still behave as acids and bases when dissolved in water. So the newer model is the Bronsted-Lowry model. It's two separate people were working on this and had basically the same idea, so they combined their ideas and named it for both of them. And it focuses on just the hydrogen ion, and it accounts for virtually all acids and bases. Any substance classified as an acid or base in the Arrhenius model will still be an acid or base in this model. So you can still look at a substance first and see, does it have H plus or OH minus to donate? And if it does, you could classify it as an acid or base. But then if it doesn't, before you decide it's neutral, look and see if it fits this model. Because some substances not considered bases in the Arrhenius model will be bases in this model, like ammonia and sodium carbonate. So acids are now defined as hydrogen ion donors. So anything that gives up an H plus when in solution is an acid. And then the hydrogen ion acceptors, whoever gets that, is the base. So the acid gives up the hydrogen ion, the base takes the hydrogen ion. And then they also talk about conjugate acids and conjugate bases. Conjugate, if you think about foreign language or English, conjugate means to change into something. So an acid, once it loses its hydrogen ion, is now going to be a base. And a base, when it accepts the hydrogen ion, is now going to be an acid. So now the reverse reaction, they've switched roles. So conjugate acid forms when a base accepts the hydrogen ion because it can now give that hydrogen ion back. And a conjugate base forms when an acid donates a hydrogen ion because it forms a base once it's lost its hydrogen ion. And we'll look at a couple examples because I know this is a little confusing. But basically, the acid becomes the conjugate base, the base becomes the conjugate acid. So acid changes to base, base changes to acid. And we think of them as conjugate acid-base pairs. So for example, your book likes to talk about it as being similar to playing catch with the ball. If you have the ball or the H+, you're the acid. If you're waiting to catch the ball or accept the H+, you're the base. So for example, HCl is an acid. HCl is aqueous, and it's put in water, which is also aqueous. And if we look at it between here and here, HCl has lost its H+. So that's why I know that HCl is an acid. And that means it changes to a conjugate base. So there's my acid-base pair. Water, on the other hand, accepts that H3+, or that H+, to become H3O+. So since it gained H+, it's a base, but it could now lose that extra hydrogen. So it now functions as an acid. So I have my acid and conjugate base pair, my base and conjugate acid pair. So my triad says, write the equation for the ionization of hydrogen fluoride in water. And as you look at this, hydrogen is going to be donated by the fluorine, so it's going to form H3O+, and that's going to leave F- before. Leave F- alone. And that's it. That's all there is to the ionization of hydrogen fluoride. So now labeling them. Why don't you pause and see if you can label these correctly. So I would label the HF as the acid because it gives up its hydrogen ion, and that means it becomes the conjugate base because it donated its hydrogen and no longer has it. Water, on the other hand, starts as the base because it gains the H+, and that means it is now the conjugate acid. So those would be the correct labels for hydrogen fluoride in water. NH3 plus H2O, I see my arrow's off a little bit, but that's okay. This one's a little trickier to write the ionization of ammonia to form ammonium, although you might remember from earlier I said the NH3 actually gains a hydrogen to form NH4+, and that leaves behind OH-, because remember H2O is really HOH. So that means NH3 gained an H+ and is the base, which means NH4 is my conjugate acid. And H2O lost the H+, making water an acid, and then OH- is my conjugate base. Now you may have noticed that water is an acid in one example and a base in another. And that's quite possible that water can serve that role in the Bronsted-Lowry definition. The last thing to talk about is this idea of monoprotic versus polyprotic acids and something called the Lewis acid base. So monoprotic and polyprotic is based off the word protic, and protic comes from proton, and that's what an H+ is. H+ is really just one proton because hydrogen with a mass of 1 has no neutrons typically. Most isotopes have no neutrons. And so it's just one proton and one electron as a hydrogen atom. But once it loses that electron and becomes H+, it's really just a proton. So instead of calling it monohydrogen or polyhydrogen, they're called monoprotic or polyprotic acids. And all it means is monoprotic means one hydrogen ion can be lost by that substance, and polyprotic means more than one. And in fact, sometimes you see the words diprotic, meaning 2 hydrogen are given up, or triprotic, 3. And you can't always tell just by looking at the formula if it's going to give up 1 or more than 1 hydrogen. There's a lot more to it than that. But if the acid's formula starts with the H, then all of those hydrogens will be lost or ionized. So when I look at my examples down here, HNO3, I can expect to be monoprotic because it'll lose that one hydrogen. H2SO4 is going to be polyprotic because it's going to lose both of those. You could call it poly or diprotic. H3PO4 is going to be polyprotic, or more specifically triprotic because it's going to lose all three. But CH3COOH, this is a tricky one. This is actually what's known as an organic acid, and it's just this hydrogen that's lost, so this one's only monoprotic. You aren't going to have to be able to identify these, but you should realize what the two terms mean, monoprotic and polyprotic. And then Lewis acids and bases, I just want to mention briefly, there's the third model for defining acids and bases, and it's really very similar to the Bronsted-Lowry model, which is used most frequently by far by chemists. Lewis acids and bases aren't used very often because the Bronsted-Lowry model works for all but just a couple of substances. But what it does is it redefines an acid as an electron pair acceptor and a base as an electron pair donor. And it makes sense because if a Bronsted-Lowry acid donates an H+, it needs a pair of electrons to become stable. So an H+ donor really is an electron pair acceptor. And if something accepts an H+, it usually is going to have an electron pair to donate. So it really is just a slightly different definition that incorporates a couple more things, but not anything we're going to worry about.